Good morning, and now we will go to the main business of our things after giving 3 lectures on reviews covering density theorems and some trace theorems and things. So, advise you to get familiarized with that, work out the problems before start studying the thing. So, let me do before weak formulations. So, I will do some inequalities first, which are important. Inequalities, and we also do and some embedding theorems, some of them recalling basically, but now we do that one, embedding theorems. So, we will state some important, not that everything will be used, but eventually it is better to understand that one. So, regarding embedding, the idea is that when you have a u in say H1, and can you get the regularity classically? Okay. This H1, H2 etc. is also a kind of regularity, but you are deeming in a growth. So, this more and more u's are defining in H1 you are demanding grade u is in L2. When you go to L2 H2 you are demanding not only the derivatives, the second derivatives. So, you are looking for the kind of regularity in the growth space. So, this is the distinction you have to understand. The LP spaces are control the integration on it, but on the other smooth classes like C, C1, C2 etc., you are looking for classical differentiability. So, these are the kind of both are smoothness in some sense in the generalized sense of when we deal with PDEs. Okay. So, you want to know the smooth function, the functions in Sobolev spaces are indeed smooth. That is one question you will ask, and you have seen some interesting result in one dimension n equal to 1, you have seen say u is in H1 of AB, that implies u is absolutely continuous. You have seen this, you have seen absolutely continuous, and you have an estimate also. So, and you have an embedding in the sense that H1 of AB is continuously embedded in C of AB, you see. So, one dimension, that the existence of distributional derivative and it is in L2 implies that function is continuous minimum, and you can estimate your the sup norm in terms of the H norm. So, the basically you are telling that then u in C of AB is bounded by your constant into nu u at H1, you see. That is an interesting, it's a kind of thing you are embedding H1 space into a C of AB space. So, you want to ask such questions for higher dimensions. So, when you go to L2 H2 2 dimensions, H1 functions are not continuous, there are examples, but if you go to more and more, so even the dimension increases, you may need more and more bigger, smaller HK spaces, means more and more derivatives are in these spaces. So, let me write down a theorem, all results when it is omega is in Rn, and all these results you can prove it using again. I am stating these results in Rn or Rn plus, where you are able to do it via Fourier transform. So, we want to write say suppose Hs, how that one. So, you are assuming S is greater than n by 2. Of course, S equal to 1 in one dimension, n equal to 1 and S equal to 1, H1 very well work. So, once you write that one, so you want to how far S is away from that. After n by 2, you look at all the integers possible, now negative integer, and then you can write anything. The remaining part, that means your S minus n by 2 is greater than 0. So, you are writing whether there is an integer. So, pick up all these integer. So, k greater than or equal to 0 integer, okay, and 0 less than or equal to alpha is less than 1. But the moment alpha equal to 1, k becomes k plus 1. So you do that one. So that's the thing you needed. Then assume V is in Hs of Rn. These things are little easy to prove. So of course it's easy in the sense that then you have a lot of results. One, so let me write, then your V is in Ck of Rn. So you see you get the smoothness up to k, whatever here. So for example, in this case say S equal to n by 2 plus alpha, k equal to 0, you just get continuity. So if you get n by 2 plus 1 plus alpha, then you get C1. So that way you can measure the continuity. So if you goes bigger and bigger k, you get the smoothness will also increase. Okay, and what does that mean? In fact, so you have this thing 2. In fact, you have little more. Okay, in fact, V is in, so not Ck, and you once it is Ck means you can define d bar beta of V for all mod V mod beta less than or equal to k. So you can get some additional information on that. So these spaces are defined even in our PDE course. Okay, Ck alpha of Rn, that is d power beta of V with mod beta equal to k is Helder continuous of order alpha. Helder continuous of order alpha, you see. And what does that mean? You have the kth derivative d power of V of x minus d power beta of V of y is less than or equal to constant into mod x minus y power alpha. So you get anything. And then there are more things, 3, d power beta of V vanishes for mod beta less than or equal to k, vanishes at infinity. This you have seen it in other cases. And so you also have the embedding in the sense that there exists constant c greater than 0 such that, so you have an embedding norm of V at Ck of Rn. What is this supernorm? It is the summation mod beta less than or equal to k of supremum of x in Rn of norm modulus of d beta of V of x is less than or equal to constant into norm of V in Hs of, so you can estimate that one in terms of the Hs norm. So that means that is Hs of Rn is continuously embedded in Ck of Rn, you see. This is the this example is precisely a special case of that one. So you can, whenever depending on this how big is your Hs, you can define that much smoothness. That is what we are trying to say that. So that is one important result. Okay. So we will go to the okay. So with that, let me do something more. And yeah, one more comment. Similar results are true for Hs not of omega, will not prove anything, or even for Hs of omega if omega smooth. Okay, you have that one. Okay. Now we are going to derive something very important, what are called Sobolev inequality. As I said, we are not going to prove this thing. So, I will state results here. So, let me write it here. So, when you have u is in W1p, say of omega, say let me do it with Rn, we will make comments later. Then you know that meaning is that u grade u is in LP of Rn, that you know. So, we can ask questions whether you can be in a bigger LP. So, the question is that can this additional information that grade u is in LP will give you u is in some L2. Can we have u is in LQ for Q bigger than P? Can we have a, but using the knowledge of thing, can we have something? And this is what the theorem, very important theorem of Sobolev inequality, there exists. It is a very leading to very interesting problem. After these results we will state some additional thing. There exists a constant C that will depend only on P and N, not on the thing, such that, positive of course, such that norm of u in LP star of Rn is, you can go up to P star. I will tell you what is P star is, constant into, careful, the very important thing is that I do not need even a term of u in LP. You can estimate, that may not be true for other things. So, you can estimate grade u of LP of Rn here. Okay. So, this is called the Sobolev inequality. So, this in particular implies your W in particular. This is actually slightly weaker than the what I wrote here, embedded in LP star of Rn. When continuous embedding of LP star of Rn only tells you that it is enough that u in LP star less than or equal to u in W1p. But what this important estimate is that you can estimate only with the derivative at P star. Okay. And what is P star? P star is called the critical exponent. I will make a command called the critical exponent. Critical in sense, when you study some compact embedding, you do not get compactness. Of course, compactness comes in a naturally, there will be boundedness of the domain, that we may think. So, the criticality comes because of the lack of compactness at P star. P star is bigger. So, what is P star? 1 by P star equal to 1 by P minus 1 by N. So, that is P star is equal to NP by N minus P. Yeah, I forgot to put a comment here. This is the case when 1 less than or equal to P less than N, very important. Okay. So, you are putting a case here. Okay. That is a very important. I will make the other embeddings when P greater than N. So, this is strictly 1 less than or equal to P less than N. Okay. So, this result is true on that thing. So, this is positive, and it is also true P star is greater than P. Okay. So, you can get, so you have your P here, you can get embedding. So, that implies that is all in LP. Now, you can use interpolation to get u is in LQ for all p less than or equal to q less than or equal to p star. Of course, for q you may not have an estimate of this form, you may need the entire W1P norm. Okay. So, so the corollary is this one. Let me write down the corollary. Maybe I will try to give a quick proof of this. Corollary W1P of Rn is contained in LQ of Rn for all p less than or equal to q less than or equal to p star. So, what do you do? Right is that, okay. So, how do you get a quick proof? I do not do the computations little bit, but I will give here. You can write 1 by q is equal to alpha by p, that is interpolation. If you have the number in between, you can write this 1 minus alpha by p star, okay, with 0 less than or equal to alpha less than or equal to 1. When alpha equal to 1, you get q equal to p. When alpha equal to 0, you get p star, q is equal to p star. So, you can write this immediately. You observe this one. If u is in LQ, that is what you want to prove it. Okay, you want to prove u is in LQ. Given that u is already know that u is in LP and u is also in LP star. So, how do you write? You write mod u minus u power. So, let me not miss anything. This one you can immediately see that you can check it. This is not immediate, right? Because you know it is in LP. So, if you take pth power of this, and it will be so p by alpha qth power, then you will alpha q alpha will cancel and cancel. You can do the same thing mod u power 1 minus alpha q is in LP star of, okay, LP star of by 1 minus alpha q. Okay. So, you are starting with here. So, you are starting with start with u is in W1P. That is what we are doing it. So, once you have in W1P of Rn, you will get it is in LP and LP star. By the main theorem, you want to prove this one. Okay. So, once you have that one, okay, it is a question of computation and some Cauchy sorts or something inequality. So, you can write your norm u at LQ power q. You can write down this is equal to integral of u power alpha q into mod u power 1 minus alpha q, you see, and apply Helder to get this is less than or equal to, you get norm u. So, at pth norm powered by alpha q into norm u at p star powered by 1 minus alpha q. Okay. And then from here you can actually derive, which let me, this arithmetic geometric mean inequality. From here you do it. LQ is less than or equal to constant into norm u at p plus norm u at p star. So, derive that. Okay. Once this is there, this is less than or equal to this, you know that it is grade u, that is constant into norm u W1P of omega. So, Rn. So, you have your Rn. So, you have that inequality. So, one more remark We will discuss about Sobolev inequality little more little later, maybe in the next lecture. The constant can be taken, it may not be the bus constant. I will talk about the bus constant maybe in the next class. The constancy appearing in Sobolev inequality can be taken as n minus 1 by n p star, depends only on p and n, like this constant you can take it. May not be the bus constant, that is a comment. May not be the bus constant. Okay. So, a couple of remarks may be more. Yeah, the results in general are not true for results in general. Result in general is not true for say W1p of omega, but true for W1p naught of omega. So, you see, when you have a you can, in this case when it is in u is in W1p naught of omega, you can extend by trivial extension. Of course, you have your trivial extension and then you get W1p of Rn, and then you can estimate and you can bring it back. So, for W1p naught of omega it is fine. Or indeed it cannot be true for a W1p of omega. For example, if omega is bounded, you see, then 1 is in W1p of omega, right, for which the grade 1 is 0. You see, you can't do. So, the right hand side is 0. So, for you see this bounded domains immediately, but for a W1p naught of omega 1 is not there. Okay. So, so the similar results can be written here for that means for u in W1p naught of omega. So, you have these results. Norm u in LP star is less than or equal to constant into norm grade u in LP, and norm of u in LQ, I write it q less than or equal to constant into norm u in W. For all q in P2 P star. So, should I do something? Yeah, I have few more minutes. So, so there are more general, so a couple of more theorems, let me write it, so then I can make something. So, yeah, so what happens when p equal to n, when p equal to n. So, what we have done is 1 less than or equal to p less than n. So, when p equal to n, and for any domain omega, any domain omega with C1 boundary, so we have, what is that? We have W1n of omega is contained in LQ of omega for all q in n to infinity. Make a remark, just a note here how P star is defined. P star is defined as NP by n minus p, 1 less than p less than or equal to p less than n. When n equal to p equal to n, we are getting P star equal to infinity. So, but you do not have the embedding at infinity. That is one remark remark which you can take, one cannot take. Yeah, so it fails. According to this the previous theorem, it would have been in q from n to infinity including infinity, but you cannot take q equal to infinity. And there are examples I will not do here, but you can work it out. Example, say for take omega is equal to b0 half. I will just state here, and you can take ux equal to log 2 by mod x or something like that, or minus whatever it is. This is not a continuous thing, it is not L infinity, not in L infinity. Okay. But you can actually prove that u is in h1 of omega. This you can work it out for exercise. Okay. So, maybe one more the final result, one more theorem, what happens when p greater than n. When p greater than n, p greater than n. So, all cases you are getting it, p greater than n, what you get it, and then omega c1 boundary, c1 means with c1 boundary, then w1p of omega. So, you need that p, the growth to be bigger to claim it is in L infinity of L infinity. You see. So, at p equal to n you do not get the point wise estimate. Okay. And you have some nice thing, depending on how big it is, you will get ux minus uy. You can have some error estimates less than or equal to constant into mod x minus y power alpha into norm of grade u at LP, where your alpha is equal to 1 minus n by p. So, you see, so you get some extra things here depending on that. You get that one. And should I do this one? Say for example, let me write it so that I do not have to continue on these embedding theorems. Example, for n equal to 3, maybe I can actually state, maybe I will skip here. So, I will continue little bit because it may take little more time. So, we will continue in the next lecture. Okay, so let me say, so I will state one more theorem. What happens to w mp of omega? What happens? So, I will just state so that it may be useful to you at some point of time when w mp. So, there is a nice interplay between, so m represents the number of distributional derivative, p represents the growth. So, there when it is more and more, it will naturally produce you the smooth functions. So the you can increase either f m or you can increase p to get the smoothness. So there is an interplay between m and p to get the smoothness. So I will state that theorem as well to get the smoothness, and then I will continue little more in the next couple of lectures. Okay. Thank you. Thank you.